I'm Dr. Meredith Barr, and I lead the EBNet Biochar Working Group. We recently held a workshop co-funded by BBNet, so I'm going to talk to you about some of the outcomes of that workshop and ideas for our future as a working group. The working group focuses on biochar microorganism interactions. So first I'm going to introduce how microorganisms can interact with biochar, and then talk a little bit about what applications these interactions are useful for. So first of all, we have adsorption. Biochar can absorb microorganisms just like it can absorb just about anything. It's considered to be a universal adsorbent because of its really high surface area. The specific morphology of biochar determines what microorganisms it can interact with, because some microorganisms might be too large to fit into some pores, for example. And that, along with its surface chemistry, which determines the strength of interactions with different microorganisms, which also have different surface chemistries themselves, allow us to design biochars that can be selective for interactions with some microorganisms that we want to target and not others. It can also act as a growth substrate for microorganisms because of the co-location of carbon, nitrogen, and micronutrients all within the biochar structure. And you might think that if microorganisms are digesting biochar, that makes it less good as a carbon storage mechanism, but in reality, the microorganisms are eating the more labile carbon fraction, which leaves behind a more stable structure that's better for carbon storage in the long run. These interactions are useful for a lot of different applications, but I'm going to give some major examples here that we have people in the working group working on. One is for engineering soil microbiomes. So we can create biochars that promote the growth of plant growth promoting microorganisms, which can in turn outcompete plant pathogens. We can do this by just using biochars that have selective properties, so morphologies and surface chemistries, and we can also use microbially enhanced biochars to seed specific plant growth promoting organisms that perhaps target a specific crop that we're trying to grow into the soil. We can also use them to clean up polluted environments, so to remediate contamination like oil spills or heavy metal contamination in, for example, soil. We can do that by generally promoting microbial growth in these contaminated environments, and then of course the microorganisms that are able to digest the pollutants that are available would outcompete others. We can also seed specific microorganisms that we know are able to degrade the pollutants that are in these environments using microbially enhanced biochars. Biochars are also often added to anaerobic digesters, and this is used to increase the biogas yield and the selectivity for methane by promoting the growth of specifically of methane-producing bacteria. And they also function to adsorb chemicals that would otherwise inhibit the growth of those bacteria. And finally, we can use biochars to clean up wastewater or to treat wastewater, either by directly adsorbing harmful microorganisms and also antimicrobial resistance genes, for example, or the chemicals that drive the development of resistance from wastewater. We can also use them as a scaffold for microorganisms that degrade chemical pollutants, so like in biofiltration, or we can add them to activated sludge systems. It was also pointed out to me recently that another great example of biochar microorganism interactions being used for a different application is to engineer the gut microbiomes of livestock. Biochar for microbiome engineering was one of the topics of the 3 sessions that we held at our recent workshop on integrating thermal, thermochemical, and biological conversion technologies to improve environmental and economic outcomes of waste and biomass valorization processes. The other sessions covered biological pretreatment of thermal and thermochemical feedstocks, so bio-first integration, and thermal and thermochemical technologies in anaerobic processes like anaerobic digestion and anaerobic fermentation. We also had an industry panel discussion where we discussed the opportunities and the challenges to taking these integrated processes and actually translating them to a commercial context. So in order to identify pathways that were particularly promising in terms of integrating these different technologies at the workshop, we used consensus activities that followed a Café Delphi format, which is a combination of the World Café, which is sort of a structured, open conversation process, and the Delphi technique, which is iterative rounds of formal surveying. So the delegates were allowed to discuss freely and propose different pathways and then vote on the pathways that had been proposed. And then those pathways that had enough votes were determined to be consensus pathways and were integrated into the ranking survey, where all of the delegates ranked the consensus pathways according to 5 criteria. So market size, ecological benefits, waste valorization, market disruption, and technology readiness level. These are the results of those consensus building activities, and I don't have time to dive into the details of the ranking survey results, but I will just quickly mention each of the consensus pathways that we identified. So for the BioFirst session, they were anaerobic digestate hydrothermal carbonization, anaerobic digestate pyrolysis, fermentation residue hydrothermal carbonization, and enzymatic hydrolysate advanced thermal conversion, which is to say just any of those thermal or thermochemical technologies that we discussed. For the biochar application session, it was contaminated soil bioremediation, microbial wastewater treatment, use in anaerobic digestion, and agricultural soil amelioration. And then for the use of thermal and thermochemical technologies in anaerobic processes, it was hydrothermal pretreatment for anaerobic digestion, then anaerobic digestate advanced thermal conversion, which of course we also saw in the BioFirst session, then the use of chars, so hydrochars and biochars in AD and AF systems, which again we saw in the biochar applications session as well, and then finally fermentation of biogas or syngas as a sort of quite disruptive new technology. So for the industry panel, we did a thematic analysis of the transcript, and we identified 4 opportunities or 4 categories of opportunities. And these were circularity and cross-industry synergies, multi-output value chains, decentralized local systems, and complementary process matching. And we also identified 6 challenges: regulatory misalignment, policy lag, knowledge gaps, market volatility, scale-up complexity, and limited industry academic translation. So in terms of the future of the working group, in order to know where we're going, we need to know who we are. So we currently have 47 members across 12 countries. 80% of our membership is from academia, but we're from diverse career stages. So we have a pretty similar number of PGRs, researchers, and academics. So some ideas for our future given that context. For the broader group, there was clearly an interest identified at the workshop in an event surrounding policy for waste utilization in the UK. So I'm thinking something like aligning UK waste valorization regulations with sustainability and innovation goals. And I'm also hoping to start sending out a more regular newsletter when the NIB funding ends. So currently I just use the mailing list for questions and updates as needed, but I'm hoping to send out something a little bit more regularly with input from the members. And if you're interested in receiving that, then you can use this QR code to sign up to that mailing list. For the core group, which by which I mean academics who are funding eligible, who are currently working on biochar microorganism interactions. A lot of our members are actually maybe working on just one or the other and interested in the interactions between them, but not necessarily currently working on that. For that core group, I'm thinking there is definitely scope for a larger collaborative funding application, so potentially a Horizon consortium. And longer term, I would love to think about forming or joining a new network, maybe something specifically around integrated biorefinery, or maybe even more biochar specific than that. So I would love to hear any ideas that the community has about the future of the biochar working group. Thanks for your time.